Hi friends, myself D.K. Narale, working as assistant professor in Gopal Krishna Gokhale College, Kolhapur. Today we will discuss the thermodynamic and kinetic aspects of metal complexes. Last video discussed about the introduction, thermodynamic stability and kinetic stability, relation between thermodynamic and kinetic stability. In this video, stepwise stability and factor affecting the stability of the complexes. These are the introduction, thermodynamic stability, kinetic stability, relation between these. In stepwise stability constant, coordination complexes are assumed to be formed by replacing coordinated water molecule by ligand molecules or ion. The different steps involved in the formation of complex can be represented as below. First step, metal with water ligand, number of water ligand plus one water ligand is replaced by one ligand. L is the confirmed in this reaction is ligand. Involve the number of steps. The second step as plus add the ligand, then the remove water molecule. Third step as similar as the K1, K2, K3 and number of step Kn. These are the equilibrium constant K1, K2, K3 and K are called as stepwise stability constant or successive stability constant for stepwise formation constant. They are called stability constant because larger their value, greater will be the stability of the complex formed at the equilibrium. Instability constant or dissociation constant is the reciprocal of the stability constant, that is k upon 1 upon k is equal to kd into bn, that is the overall formation constant for overall stability constant is the product of the stepwise stability constant, that is bn formation of constant is equal to k1 into k2 into k3 dot dot a number of kn. First, m plus l according to law of mass action, m plus l k1 m l, that is therefore k1 is equal to ml upon, that is product divided by reactant m into l. Similar ml plus l k2 then ml2, therefore k2 is equal to ml2 upon ml into l. Next, third step, the ml2 plus l k3 ml3, therefore k3 is equal to ml3 upon ml2 into l. If n is equal to 3, then bn, that is overall formation constant, is equal to k into k1 into k2 into k3, then bn is equal to ml upon m into l into ml2 ml into l into ml3 ml2 into l. By rearranging, bn3 is equal to, the rearrange the equation, then after cancellation ml 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 ml2 cancel, then bn3 beta 3 is equal to ml3 upon m into l cube, that is bn is equal to k1 plus k2 plus k3. Thus one can write beta n overall formation constant in general bn is equal to ml n divided by m into l into square. For the system having the nth steps, here note that square indicate actively generally in the term of concentration. Overall stability constant is measure of stability of the complex. This value may be ranges from 10 raised to minus x into 10 raised to plus x, where x may be in the range of 1 to 15. To account this value of beta n are frequently given on logarithm scale. P beta n is equal to log base 10 to beta n. Therefore, log base 10 beta n is equal to log 10 k1 plus log base 10 k2 plus log base k3 dot log 10 kn. As roughly measure value of Pbn greater than 8 may be represented stable. The complex is stable. Greater than 8 the beta n. Then the further beta n can be related with the standard free energy chain delta G0 enthalpy, delta H0 and delta S0 entropy. Following equation. Factors affecting the stability of complex. Major two factors: nature of metal and the nature of ligands. In nature of metals, number of point, the first is the charge. More the charge on central metal ion, greater will be the attraction of the ligand, and hence higher will be the stability of the constant. It is clear that log k value almost double, then the stability constant stability increases accordingly. Fe2 plus Fe3 plus, then the 14 log k value of 14.3 and Fe3 plus shows the 2.5. Charge is double, then the increase the log k value, then the complex will be more stable. At the same time, less electropositive elements, that is class B metals, form stable complexes with less electronegative elements like the chlorine, sulfur and phosphorus. It could be explained on the basis of polarizing power electronegativity. Second, size of metal. Stability of complex increases with decrease in size of metal. Size is assumed in terms of radius of central metal ion. Thus, the charge to radius ratio may play important role to determine the stability constant. Third, charge to radius ratio. If the central metal ion has higher charge and the smaller radius, that is, if charge to radius ratio more, then stable will be the complex. The charge to radius ratio is also called ionic potential. If charge remains constant and size increases down the group, the stability of complex will be fixed and ligand decreases down the group. Then Li plus Na plus K plus Rb plus Cs plus. Second point, Cu plus forms stable complex than the K plus. D, crystal field stabilization energy and stability. Crystal field stabilization energy has certain effect on the stability. It is observed on the irrelevance graphs. The terms log k versus atomic number of dipositive cation similar to crystal field stabilization energy clearly indicate that higher the value of CFC, more stable will be the complex. This the atomic number increases from 20 to 30. Then it increases the log k value, then the decreases at stable electronic configuration will be the decrease the crystal field stabilization energy or log k values. Nature of ligand. Second factor, nature of ligand. In first, charge and size. More charge and smaller size of ligand may form stable complex. Example, fluorine forms the stable complex with the many metals, that is more electronegative and more charge. The second, the halide complexes of many metals have been studied. For most of the metals, sequence of stabilities, that is F minus, Cl minus, Br minus, I minus. But this order may be reversed in the metal. Here there is chance for back donation of electron density to ligand, metal to ligand, back donation of electron. However, several atoms constitute most of the ligand, and one can consider the size of ligand, not radius. Example, chloride ion, perchlorate ion has very small tendency to form complexes. B. Dipole moment and polarizability. During complex formation, there is a electrostatic attraction between metal and ligand. More polar the ligand, higher will be the attraction between metal and ligand. Thus, stable will be the complex formed. C point, basicity of the ligand. Basicity is the measure of electron pair donation. Higher the basicity of ligand, more stable will be the complex formed. Effect of ligand basicity on Ag plus complex. Here note that interaction increasing the log K value clearly support the relationship between ligand and basicity and stability of complexes. These are the ligands. Ligand then increases the basicity, log K value also increases. Next, pi bonding. Pi bonding is specially formed by back donation of electron density by metal to ligand, form stable complexes. Example, ligand having vacant orbitals capable of forming pi bonding, that is trimethyl phosphine sulfide iodide COCN. These are the by back donation of metal to ligand, pi bonding donation. Third, crystal field effect. Next, crystal field stabilization energy plays important role formation of stable complex. Higher the CFC, more stable will be the complex formed. Example, CO is neutral ligand but still split d orbital more, delta value higher, and hence form very stable complexes with many metals. It may be because of the pi, its pi bonding capacity, accepting back donated electron by metal. This is well explained by spectrochemical series. Next factor, steric factor. If there is a substitution of bulky group either on donor atom or near of the ligand, then the stability decreases due to steric hindrance. Here, not that more steric hindrance because of substituted ligand is observed, and hence decrease the stability. In the example, bulky group is substituted near donor atom N, and hence stability decreases. Here the substituted Ni and CO complexes, beta, log beta value metal complexes, oxygen, substituted oxygen shows it decrease the value. There is a simple ligand amine, then substituted, oxygen to methyl oxygen. Next point is stereochemical requirement of ligand also affect the stability of complex. Example, ethylene diamine trine form a stable tetrahedral complex and unable to form square planar complexes, while triene is more suitable for square planar complexes than for the tetrahedral complex. The common stereochemistry of Ni2 plus is square planar, and it may be prepared triene or trine and triene. Zn2 plus prefer trine and triene because it's a more preferred stereochemical rearrangement of tetrahedral sp3 and no d orbital available. Thus, stereochemical requirement also play important role of Ag NH amine diamine silver is more stable than the mm, ethylene diamine Ag silate because Ag trends for linear complexes and 5-membered ring. These are the chelating and these are the complex. Chelating complex and this unchelating, that is the complex is formed only. This 5-membered ring form is more stable is the AgEn complex. Chelating effect. Complexing containing chelate ring shows extra stability than the similar complex without ring. This extra or higher stability is known as chelate effect. Here in both complex A and B, central metal atom is Cu2 plus, donor atom are 4 nitrogen. Charge on the complex is the same 2 plus, but only difference is the ring structure in B, and hence it is more stable than A. The chelate effect can be explained on the basis on entropy change. This 1 plus 2 1 plus 2 then gives 1 plus 4 1 plus 4 5. 3 mole of reactant produces 5 mole of product. That means increase in particulate forms 3 to 5 result that in positive entropy changes, which terms added to negative enthalpy value to give more delta G value. Delta G0 is equal to delta H0 minus T delta S0. That is delta G0 is equal to minus RT ln K. Thus from the equation 1 and 2 it is crystal clear that more the entropy positive, higher will be the stability of complex. Stability of complex depends upon size of ring. 5-membered ring is more stable than the other number. 5-member is log K value 10.7, then 6 7 8 is less log K value. More the log K value, more will be the stable of the complexes. In EDTA calcium EDTA chelate, less number of atom or more than 5 or 6 number of atom in the ring of complex decrease the stability because of the strain. Also higher the number of 5-membered ring in the complex, more stable will be the complex. EDTA complex, in EDTA complex 5 rings 1 2 3 4 and 5, that is this complex is more stable because of the 5-membered 5 ring in from the complexes. Thank you for listening and watching.